The alternating series test, part 1. Consider the series, the sum of a sub n, where the terms of a sub n are finite, positive, and decreasing to 0. This is one way that we write decreasing, and often we can write it like this, decreasing to 0. So if we have a series like this, and then we take our positive terms and make them alternate, then this new alternating series test will converge. And this is called the alternating series test. Now, one thing I want you to remember is that if a sequence decreases to 0, that does not mean that the series will converge, unless it's an alternating series. The other note I want to point out is that the alternating series test is for convergence only. Let's take a look at an example. What if we have the series n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n. The n plus 1 is just another way of writing it, but this makes it alternate. Side note, this is called the alternating harmonic series. Just in case you see that notation somewhere. Well, let's look at the sequence 1 over n. As n goes to infinity, certainly 1 over n decreases to 0. And since the series in question alternates, we know that this series will converge by the alternating series test. It's that simple. Now, in practice, on a test, your professor might want all the details saying a sub n is finite, positive, and decreasing to 0. Perhaps that notation will be necessary, but here we're getting the idea. Before I get to this next example, let's consider the harmonic series that is 1 over n that does not alternate. And recall that this series will diverge by the p-series test. Which means our original series converges only because it alternates. We'll get to that just a little bit later. But let's take a look at this example here. I have an alternating series because I have the negative 1 to the n. Let's look at the sequence part. Let's do the limit as n goes to infinity of just the sequence part, 2n plus 1 over 3n plus 4. And notice that that goes to 2/3, which does not equal 0. Which means that this series diverges, but not by the alternating series test, because the alternating series test is for convergence only. Instead, this diverges by the nth term test, which I like to call the nth term test for divergence. So if you have an alternating series, it'll either converge by the alternating series test or diverge by the nth term test. Now let's go back to an earlier thought that I proposed. that I want to answer right now. So I'm going to write down some series. They're all going to be alternating, and all of them will converge. I want you to ask yourself as we go along, which of the series converge only because they alternate? Which of the series will converge even if they didn't alternate? First example, we'll do n equals 0 to infinity of negative 1 to the n over n squared. If I look at 1 over n squared, I have terms that are decreasing to 0. So I know that this definitely converges. I'm going to leave a little space here for later. But if I consider the series that doesn't alternate, that is, if I took away the negative 1 to the n, I know that this would converge anyways. In this case, by the p-series test. Okay, so this converges regardless of whether or not the series alternates. Let's take a look at our next candidate. I do n equals 0 to infinity, and I'm going to do the cosine of pi n over n plus 1. Now confirm that this alternates. So the cosine, let's plug in n equals 0, I would get the cosine of 0, which is 1. So again, I'm just going to look at the top part to confirm that the top part alternates. If I plug in n equals 1, I get the cosine of pi, which is negative 1. N equals 2, cosine of 2 pi is positive 1, and you can see that the top part alternates back and forth. So this is another kind of sneaky way of writing an alternating series. 1 over n plus 1 decreases to 0, so I know that the series converges. But what about the series 1 over n plus 1 that doesn't alternate? I know that this one diverges. You have a couple choices. You can either do the integral test, or I would do the limit comparison test personally. But either way, I know that that series converges only because it alternates. So a couple definitions for you. A series that converges on the condition that it alternates converges conditionally. Well, that's where we get the term. A series that converges on the condition that it alternates converges conditionally. A series that converges even when we make all terms positive, that is, if we were to take the absolute value of the terms, that series converges absolutely. So let's take a look at just a couple more examples. I'm not going to go through all of the work to show you what happens. I will leave that for you to confirm. But we have an alternating series whose terms are decreasing to 0. So I know that this converges. But I also know that this will converge even if it didn't alternate. So that series will converge absolutely. If you want a hint, I guess I'll get you started. This would be the ratio test. How to know it's the ratio test? I have factorials, giant clue. Well, as long as I'm here, let's go and finish this one off. I have the limit as n goes to infinity of e over n plus 1. As n goes to infinity, this goes to 0. So I know that it converges. Notice, absolutely. One final example has to do n equals 1 to infinity of negative 1 to the n times n squared plus 2 over n cubed plus 2n. My terms decrease to 0. So I know it converges. But what if I took away the negative 1 to the n? That is, what if I found the absolute value of the terms? Would this still converge? The answer is no. And this would diverge by the limit comparison test to the series 1 over n. So this series converges, but only on the condition that it alternates, which means the series converges conditionally.